Hi there. This video is going to introduce you to the concept of molecular polarity. We've already talked about how individual bonds in a molecule can be polar or nonpolar, and now we're going to talk about how we determine whether or not the overall molecule itself is polar or nonpolar. For this, we need to take into account all of the bonds in our molecule and decide whether or not all of the dipoles that may be present in a molecule cancel each other out, or if there's an overall dipole moment. Before we get into predicting polarity of molecules, let's take a look at what it means to actually be a polar molecule. The consequence of being a polar molecule means that when you turn an electric field on, molecules will orient in the direction of the charged plates. Okay, so if we look here on the left side where we have no electric field on, molecules will just kind of float around in space randomly oriented to those plates. But if we turn on an electric field and these plates become charged, so here we have a negative charge and here we have a positive charge, polar molecules will orient themselves. So you'll notice that instead of being randomly oriented like they are over here, now all of our molecules have a directional behavior, okay, where their partial positive charges would align with the negative charged plate, and the negative partial charges would align with the positively charged plate. This sort of behavior obviously has consequences for when you have molecules in the vicinity of an electric field, like a magnet. You'll also see down the line, as you go further in chemistry, that polarity of molecules will have an effect on how they interact with electromagnetic radiation. It turns out that polar molecules, molecules with a permanent dipole moment, are what we call IR active. So if they have a permanent dipole moment, that makes them potentially able to interact with IR light, which induces vibrations in a molecule, which is actually one of the reasons why we have greenhouse gases. It's that interaction of polar molecules with IR light that creates the heat that we associate with greenhouse gases. Okay, so let's move on and see if we can start being able to predict whether or not a molecule is going to be polar or not. Now, as one of your tools that you're going to want to have handy, make sure that you have access to your electronegativity table, okay, or are at least thinking about relative electronegativities of your atoms. Okay, so remember electronegativity increases going toward fluorine. Okay, so going left to right and bottom to top. Okay, so when looking at the overall polarity of a molecule, we're essentially asking ourselves who wins the electron tug of war. Okay, so for molecules that have more than one bond in them, we want to look at the individual dipoles of each individual bond in that molecule, and then ask ourselves, is one of those bonds going to be pulling on electrons more than the others, creating an overall uneven distribution of electrons in the overall molecule? Okay, so let's take our first molecule over here. This, you might recognize this as methane. Okay, so this is CH4. All right, so we have our carbon and 4 hydrogens oriented around that carbon. Okay, so the first step in predicting polarity will be to look at the individual, what we call bond moments within the molecule. So we want to look at the overall dipole moment of each bond in the molecule. Okay, so this is where we want to look back at our electronegativity table. If you don't remember the relative electronegativities between carbon and hydrogen, just go back here and look for hydrogen. Okay, we have an electronegativity of 2.2, and for carbon, we have an electronegativity of 2.55. Okay, and just looking at their relative positions on the table, we see carbon is closer to fluorine. That's probably going to be our more electronegative element between the two. Okay, so carbon is going to get our partial negative charge, and hydrogen will get our partial positive charge. So we can indicate that on our bond moment. Use a little bit of a brighter color here. Okay, so we can indicate that. Oops, I'm drawing it the wrong way. All right, so catch yourself, don't go on autopilot. Okay, so we're going to draw an arrow toward the more electronegative elements. So we just said carbon is going to be more electronegative than hydrogen, and then we'll put a little plus sign on that arrow for the hydrogen. So that's another way to designate your partial positive and your partial negative. Okay, so we do our bond moments with arrows that look like that, where you have the little kind of positive crosshair for the partial positive side, and then the arrow points toward the more electronegative atom. Okay, so we have one of those for every bond in our atom. So we can do that kind of picture. We have another one there, and then our fourth one there. Okay, so we see that we have 4 essentially equal bond moments in our methane molecule. All right, so the next thing that we want to ask ourselves is, will these bond moments cancel each other out? Okay, are they all kind of pulling equally in a symmetric way in this molecule? Or is there a little lopsidedness, unevenness, asymmetry, however you want to think about it, that might skew the relative pull of electrons in our molecule? This is where it's important to be able to correctly identify the overall molecular geometry of your molecules. Okay, so this is a skill that we've been developing recently. Okay, so this is where you're going to put that new skill of predicting molecular geometry to work for you. Okay, it's really an important step in predicting the overall polarity of your molecule. So if you went through drawing a Lewis structure for methane, and then going through the VSEPR, your VSEPR theory for predicting molecular geometry, you would find out that, or you would determine that methane has a tetrahedral geometry. Okay, and the thing to remember about tetrahedral shapes is that they are completely symmetric. Okay, so tetrahedral is one of our symmetric geometries. Okay, if you have all of the same atoms, if you have all of the same things around your central atom as we do here, everything's a hydrogen, okay, that's going to make for a totally symmetric molecule. So each one of those individual bond moments, if we think about it like a tug of war between all of those hydrogens pulling on that carbon, none of them are actually going to win because they're all pulling with exactly the same strength on that carbon. Okay, so there's no part of that molecule that's going to be distorted or asymmetrical in terms of how the electrons are distributed. Okay, so this would be what we call a nonpolar molecule. Okay, so that's totally symmetrical. Okay, so even though we've said that our tetrahedral geometry is one of our symmetrical geometries, okay, that's only the case, remember, for when everything coming off of your central atom is exactly the same, okay, or has the same electronegativity value, okay. Once you change one of those atoms, okay, so let's say maybe you have a lone pair there instead, or in this case over here, we've substituted it with a chlorine. So this molecule over here is CH3Cl. Okay, so we've just substituted one of those hydrogen atoms for a chlorine. Okay, you can just visually looking at this, you can see that everything has changed now. We no longer have a totally symmetrical molecule. So this is probably going to be a polar molecule, just looking at our picture. Okay, but we can double check that. Again, go back and look at your electronegativity table, and you're going to look and see if the chlorine, so remember this is a Cl, okay? You're going to compare the electronegativity of chlorine versus the hydrogens, okay? And if it's different, then you know that it's going to pull on those electrons a little bit differently than the hydrogen atoms. Okay, so let's go back over here. So we want to find chlorine. So chlorine is over here, much closer to fluorine than our hydrogen. Okay, so looking at electronegativities, we have 2.2 versus 3.16. So chlorine is much more electronegative than the hydrogen, so it is going to tend to pull on those electrons more strongly. Okay, the other thing we want to look at while we're here is what is the relative electronegativity of chlorine to carbon? Okay, so chlorine also has a higher electronegativity than carbon. So let's see how that affects our bond moments. Okay, so remember we want to draw our individual bond moments for every bond in our molecule. So we already know that our hydrogens are oriented this way, with our hydrogens being more positive, carrying that partial positive, because carbon is more electronegative than the hydrogen, right? So we have the same situation there. But we just said that chlorine is actually more electronegative than hydrogen, so that bond moment is going to point toward the chlorine this time rather than the carbon. Okay, so if we add up, if you're used to doing any vector addition, okay, you'll essentially be doing your point to tail vector addition would work here if that makes sense to you in a mathematical way. Okay, but otherwise you're just kind of picturing where is the overall pull of electrons going to go. Okay, so in this case, everything's kind of going to be pointing toward that chlorine. So we'll see an overall molecular dipole essentially pointing this way. Okay, so this would be our overall molecular dipole. Okay, so in this case, our individual bond moments do not cancel out. Okay, chlorine is actually going to win the tug of war. So essentially, you can think of this as wins the tug of war. Okay, all the electrons are kind of going to be moving toward the chlorine. We get an overall dipole moment facing this direction, okay, which means we have a polar molecule. All right, and as you get more familiar with using Spartan, okay, you could have Spartan do calculations of dipole moments for you. So if you did a dipole moment calculation in Spartan for methane, and then did one for CH3Cl, okay, you would see that Spartan would give you an overall dipole moment of 0 for CH4, so we would write that as mu is the symbol for dipole moment, so mu equals 0. Okay, so that's our symbol for dipole moment. Has units of debye, if you see that around anywhere. Okay, and then you would have a overall dipole moment greater than 0 for a polar molecule like CH3Cl. Okay, so Spartan would actually calculate numerical values for that dipole moment in units of debye. Okay, but as far as you're concerned, just predicting polarity using your molecular geometry and electronegativities, you would just be making a conclusion of whether something is polar or nonpolar. You could probably put them in relative ranges, okay? So depending on how much of a difference in electronegativity you have for the bond moments that are coming off of your molecule, okay, you might be able to order things in general orders of larger dipole moment versus smaller overall dipole moment. Okay, but if you want explicit values, you're going to need to be doing some experimental measurements or some calculations using Spartan. Okay, so let's put some of our new skills into practice today. So why don't you pause the video for a few minutes and try your hand at predicting whether or not these three molecules will be polar or nonpolar. Okay, so this is going to allow you to practice drawing a Lewis structure, predicting your molecular geometry, predicting the individual bond moments, and then predicting the overall polarity of your molecule. So there's a lot of skills that you're putting into use in answering this question of whether a molecule is polar or nonpolar. So this will be a good test for you in working with those skills. So pause the video for a few minutes, try and attempt at all of these molecules, and we'll check back here and see how you did. Okay, hopefully you've tried your hand at each of these, so let's walk through how we would tackle this. All right, so for carbon dioxide, first step in drawing a Lewis structure is to figure out the number of electrons that we have to work with. So we get 4 valence electrons from carbon and 6 from each oxygen, which gives us a total of 16 electrons. Okay. All right, so let's draw a Lewis structure for CO2. So carbon's going to go, this is our central atom. The least electronegative one goes in the middle. So we're going to have carbon and then 2 oxygens around it. Okay, the best way to place those electrons is going to be with 2 double bonds and 2 lone pairs on each oxygen. So let's double check our electron count. So we have 2, 4, 6, 8, 10, 12, 14, 16. Okay, so I've used the appropriate number of electrons, and we double check our octet. So oxygen has access to 2, 4, 6, 8. Carbon has access to 2, 4, 6, 8, and oxygen has access to 2, 4, 6, 8. Right, so remember each line represents 2 electrons. Okay, so I feel good about this Lewis structure. Okay, hopefully this is what you ended up with. Now it's time to use our Vesper theory and predict our molecular geometry. Okay, so if you look at your table of molecular geometries, you would see that if you have 2 things coming off of your central atom, okay, that leads us to a linear geometry. Okay, so this is going to be a linear geometry. Okay, so we can leave it the way that we've drawn it here. Now we want to take a look at the individual bond moments for this molecule. Okay, so if you look at your electronegativity table, or remember where these are positioned relatively, you'll see that your oxygen is the more electronegative atom. So our bond moments are going to be oriented like this, with the negatives toward the oxygens and the positive toward the carbon. Okay, so now we ask ourselves, are any of these bonds going to win the tug of war in this linear molecule? Okay, so we have essentially exactly the same difference in electronegativity for those bond moments. They're pulling opposite from one another. Neither one of them can pull any stronger than the other. So we will say that these are essentially going to cancel each other out. Okay, so this molecule would be nonpolar. So your dipoles cancel, or bond moments, if you want to be specific. Okay, so one thing to keep in mind is that we'll see down the road that your carbon dioxide can actually do some different motions rather than just along that linear way. Sometimes it will bend, okay, or have some asymmetric stretching, as we call it, and that's where it will get some changes in its overall polarity, which makes it an active greenhouse gas. So just some fun trivia for down the line to keep an eye out for. Okay, let's move on to phosphorus pentachloride. Okay, so again, hopefully you can start to put your naming together, right? So we start with our central atom, and then we have 5 chlorines around it, so it gets the penta prefix there. Okay, so we have 40 electrons for our PCl5 molecule. Okay, so 5 coming from the phosphorus and 7 coming from each of the 5 chlorines. So add those all up and we get 40 electrons. All right, so let's draw our Lewis structure. Okay, so again, we have our phosphorus surrounded by our chlorines, 3, 4, 5. Just start out by putting them symmetrically around your central atom. We'll figure out the geometry in a minute. Okay, so if we want to have 40 electrons in this molecule, okay, let's start by putting octets on all of our chlorines. So many dots with the halogens, huh? Okay, so everything now has an octet. Phosphorus is actually an expanded octet right now. Okay, but let's double check our electron count and see where we're at. So we get 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Okay, so everything, all of our chlorines have an octet. I don't need to share any electrons to give anything else enough electrons. Okay, we don't need any multiple bonds in here. So this Lewis structure looks good. Okay. Step before we can predict polarity. Okay. Don't rush the gun here and say this is a totally symmetrical molecule because of the way that you've drawn it in 2 dimensions here. Remember, your Lewis structure doesn't tell you anything about the 3-dimensional structure of your molecule, so we still need to do our Vesper theory. Okay, so if you look at your table of molecular geometries, okay, you're looking for the column where you have 5 things coming off of your central atom. Okay, that should lead you to a trigonal bipyramidal geometry because everything coming off of that central atom is an atom. Okay, we don't have any lone pairs. Okay, so we are with our trigonal bipyramidal geometry. Okay, so now if you picture that trigonal bipyramidal geometry, it will be helpful for you to go look at the 3-dimensional figures or examples of a trigonal bipyramidal if you can't picture this in your head yet. Okay, that's fine, but you should see that that's a totally symmetric geometry if everything around your central atom is the same thing, okay, which it is in this case. So this is going to be totally symmetric. So let's do our bond moments just to be thorough here. Okay, so again, chlorine is more electronegative than phosphorus, so our bond moments are all going to be pointing toward our chlorine. Okay, they're all going to be pulling at the same strength in a totally symmetrical geometry, so this is going to also be nonpolar. Okay, on to our final example of sulfur tetrafluoride. Okay, so again, we've got our central atom comes first, and then we've got 4 fluorines, so it gets the tetra prefix. Okay, so you should determine that we have 34 electrons in this molecule. Okay, we've got 7 electrons coming from each of the 4 fluorines and 6 from the sulfur. Okay, so we get a total of 34. So let's draw our molecule. So running out of room here. But again, just kind of put those symmetrically around your molecule for your Lewis structure. Everything gets an octet to start, and we'll see where we end up with our electron count. Okay, so let's do our electron count. Everything has an octet right now. Okay, so we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, so we've got 32 electrons in this molecule right now that give everything an octet, which means we have 2 electrons left over to get us to the 34. So hopefully you remember to dump those 2 extra electrons on our central atom. They're going to go on the sulfur. So we get a lone pair in addition to the atoms around our sulfur. Okay, so now we predict the geometry. Okay, so you're looking for the column in your table or the row in your molecular geometry table that has, again, 5 things coming off of your central atom. Okay, so we have 4 atoms, the 4 fluorines, plus a lone pair. So that's a total of 5 things coming off of your central atom. Okay, so similar to our situation here, okay, except one of these atoms is now a lone pair. Okay, so we're still going to be in that overall trigonal bipyramidal electron pair arrangement around our central atom, okay, except now we have to move over to the column where we have 1 lone pair. Okay, so that should take you to the seesaw geometry, okay, which again falls under our trigonal bipyramidal overall electron pair arrangement. Okay, so this is a subset of your trigonal bipyramidal. Okay, but we have a seesaw geometry. Okay. All right, so let's look at our bond moments. I'll change the color here because it's a little hard to see with everything blue. Okay, fluorines obviously are going to carry that partial negative in our bond moment. That's our most electronegative element. Okay, so whenever there's a fluorine, you know those arrows are going to point to that fluorine. Okay, and also remember lone pairs, you don't often see this drawn depending on the resource that you're looking at, but remember those electron pairs are very negative, right? Those are just negative electrons. So you could think of this lone pair also as pulling a lot of the negative charge, okay? And it's going to do so differently than the fluorines do, okay? So if you look at your seesaw geometry, okay, if you look at the 3-dimensional structure of the seesaw geometry, it's very clear that that's not a symmetrical geometry, right? So this is not symmetrical no matter what's around it, okay, because you have that that lone pair in there causing you to have a very asymmetrical molecule, even if all of these are the same atom. Okay, so here we know that we're going to get an overall dipole moment. So this is going to be polar. We could also say mu is greater than 0. Okay, we would also say mu is equal to 0 if you wanted to, is another way to say that those are nonpolar. Okay. All right, so hopefully this was helpful in getting you some practice with your Lewis structures, predicting your geometry, and then with our ultimate goal of predicting whether or not you have a polar or nonpolar molecule. Okay, so remember the real trick is just being able to predict whether or not the overall geometry of your molecule is symmetrical or asymmetrical. Okay, is part of your molecule going to win the tug of war over another part of your molecule, or is everything kind of pulling equally around your central atom? Okay, so those are the skills that we're trying to develop here. So keep practicing, and hopefully you found this helpful. All right, thanks.